A very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course. So today's classroom discussion topic are first one is entropy and disorderness, and the second one is third law of thermodynamics, and the third one is available energy and unavailable energy concepts. What is the motivation behind these particular topics? So it is very essential to know about how entropy is related to the disorderness or the randomness of the molecules or the system, and how can we define the third law of thermodynamics and what is its importance, and how can we define the available energy and unavailable energy in this lecture. So this lecture is having the outcome. So the learning outcome is at the end of this lecture, you should be able to define the third law of thermodynamics, available energy and unavailable energy. So let us see first of all the first topic, that is entropy and disorderness of the system. So because we studied that entropy is basically, it is a measure of the randomness of the molecules or the disorderness of the molecules. So disorderness or the randomness of the molecules is basically measured by the entropy. If the disorderness of the molecules is very high, so then automatically the entropy of the system is also very high. So that is, whenever the disorderness is goes on increasing, so automatically we can say that the entropy of the system or the universe also increasing. So that's why just you go through this figure. So entropy is defined as a state of disorderness or the randomness. In general, the universe tends to move towards release of energy, and that leads to the greater entropy. So another example here you can see the spontaneous chemical processes often result in a final state is more disordered or random than the original. Absolutely. So whenever there is a chemical process is taking place, automatically there will be more disorderness of the molecules will taken place. So the entropy of the final state always it will be higher than compared to the initial state. So the spontaneity of a chemical process is related to a change in the randomness. So that's why entropy is a thermodynamic property related to the degree of randomness or disorderness in a system. So that is concluded, that is entropy is basically related to the disorderness of the system. And what factors are basically affecting the entropy? So the first one, the entropy depends on temperature. So just now we studied that whenever you are heating a working fluid or whenever you are heating a particular gaseous substance, so automatically the disorderness of the molecules will be increases. So that is, the orderedness of the molecules will be disturbed whenever you are heating. So automatically it will be separated, it will move in the random motion. So that's why automatically the entropy will be increases. So the same thing I have written here, entropy depends on temperature for any substance. So the entropy value will increases as the temperature will increases. The next parameter is entropy depends on the physical state of a substance. That is important one. So that is whenever you are having the three phases like solid phase, liquid phase and the gaseous phase. So in the earlier lectures also I told you that. So whenever we are having the three phases, so in which phase the entropy is minimum. So that is just you can see here. So that is in the solid state the entropy value is less. Next, liquid and the gaseous phases the entropy value will be very high, because the structuredness of the molecules or the orderedness of the molecules in case of the solids, it is something orderly spaced. So, but whenever you are going to the liquid, somewhat disturbed. But in the gaseous phase is a more randomness of the molecules. So that's why the entropy of a solid state will be the lowest, then the liquid, then in the gaseous phases it will be very high. So the formation of a solution also affects entropy, and it is also related to the atomic size and molecular complexity. So like that, these are the factors which are basically influencing the entropy concept. Now we can see here. So visualizing the effect of temperature on entropy, because just now I said that Whenever you are increasing the temperature of your working fluid, so automatically the disorderness of the molecules will increases. So that leads to the entropy concept. That is, the entropy value also increases. So now just you see here, is the less freedom of the motion, fewer microstates, and whenever you are heating, so that is just you are able to observe the higher temperature, more freedom of the motion, more microstates, and that leads to the higher entropy value. So due to the heat transfer, that is you are transferring heat, means that is the higher heat input, that is the temperature is increasing. So automatically just you see here, it is the less freedom of the motion, and here you are able to have the more freedom of the motion of the molecules you are able to observe. And similarly, the another example also here, so it is whenever you are heating higher temperature, so more microstates you are able to observe, that leads to the higher entropy value. So that is a conclusion. That's why the entropy is a measure of the disorderness of a system, and natural processes tends to move toward the state of the greater disorderness because all are taking place according to the irreversible process. So for an irreversible process, entropy of the universe always increases. So here I have quote you some example. Just you go through that particular the example once again. It is taking place to the irreversible process. Next, the concept is the third law of thermodynamics. So far, we completed the zeroth law of thermodynamics, first law of thermodynamics, and second law of thermodynamics. So the remaining one is the third law of thermodynamics. So how can you state the third law of thermodynamics? It is very, very important one. It is impossible to reach a temperature of absolute zero. So on the Kelvin temperature scale, that is at absolute zero temperature value is nothing but is a 0 Kelvin or minus 273.15 degrees centigrade. So that can be treated as an absolute zero temperature. So here at absolute zero temperature, we can say that the entropy value is equivalent to zero. That is the meaning of the third law of thermodynamics. So here there is a decrease in the temperature. Just you go through this particular diagram. Decrease in the temperature, decrease in the kinetic energy. More decrease in the temperature, so more decrease in the kinetic energy. And whenever you are going to the absolute zero temperature, just now I told you that is a 0 Kelvin or minus 273.15 degrees centigrade. So absolutely the kinetic energy will becomes zero. That is more ordered way of the molecules. So here the disorderness is something, it is very, very high, and now it is somewhat reduced, and here it is totally reduced because of zero kinetic energy. So because of the structuredness of the molecules or the perfect order molecules, we can say that the entropy value is zero at absolute zero temperature. That is the meaning of the third law of thermodynamics. So that is here we can say, so that is entropy of a perfect crystalline substance at 0 Kelvin, that is at absolute zero temperature, is zero. What is the reason? Because no entropy means, so there are no disorderness of the molecules. That is, it is highest order possible. That is, highly orderly placed molecules are there. So that's why we are not having any entropy value at absolute zero temperature. So that is the meaning of the third law of thermodynamics. So what do you mean by the perfect crystalline substances? Just you can see here. So perfect crystal at 0 Kelvin, that is a positive node and negative node. And here there is a disturbance is taking place whenever the crystal deforms at a temperature more than the 0 Kelvin. So it is a perfect crystalline substances at absolute zero temperature, entropy value is zero, and whenever it is deforms higher than 0 Kelvin, so disorderness of the molecules increases, so it leads to the entropy higher. So that is once again the entropy of a pure crystalline substance at absolute zero temperature is zero. So that is the meaning of the third law of thermodynamics. The same thing I have written here, that is this is the comparison of the solid state, liquid state as well as the gaseous state. And I've already told you that in the solid state we are having the minimum entropy. When we go to the liquid, the entropy value increases, and whenever further we go to the gaseous state, the entropy value is further increases. That is the comparison between the solid state, liquid state as well as the gaseous state. And next, after completion of the entropy concept, now we are entering into the third topic of the classroom discussion, that is available energy and unavailable energy. So available energy is also known as the exergy. So nowadays there is a lot of research is going on the exergy analysis. So exergy is nothing but is available energy. So that is whenever we are having the total energy. So total energy is basically defined as it is the summation of available energy plus unavailable energy. That is that energy will be split into the two ways. The first portion is known as the available energy and the second portion is known as the unavailable energy. And whenever we are summing up these two, that is basically called as the total energy. So available energy is known as the exergy and unavailable energy is known as energy. Energy. Exergy plus energy is equivalent to energy. So now how can we define the available energy? Because the today's classroom discussion is only limited to the defining available energy and unavailable energy. In the next classroom discussion topic, we will discuss in detail about the available energy and unavailable energy concept. So it is very, very important one, how to define the available energy. So available energy, it is a maximum portion of the energy which could be converted into the useful work. That is very, very important one. So it is a maximum portion of the energy. That is whenever we are giving some Q1 amount of the heat to the heat engine. So out of that particular the Q1 amount of the heat input to the heat engine. So that heat engine should be in a position to convert it into the maximum useful work by dissipating very least amount of the heat rejection, because heat rejection should be there. We cannot avoid the heat rejection, but the heat rejection value should be minimized because the W is equivalent to Q1 minus Q2. So whenever the Q2 value is lower, so automatically we are able to have the higher amount of the work done. So W max is equivalent to Q1 minus Q2. So Q1 is basically the heat input is constant, and whenever the Q2 value is less, so automatically the W value will be higher. So we have to search, because as an engineers, so always we have to think about the mechanism to have the higher the useful work which can be obtained from a particular device or from a particular system. So now it is very, very important one. Available energy is nothing but is a maximum portion of the energy which could be converted into the useful work. And similarly, the unavailable energy is nothing but how much amount of the heat is rejected by the heat engine. So just now I told you that is a Q2 amount of the heat is rejected by the heat engine. So that is it's the unavailable energy. So the summation of available and unavailable energy which leads to the total energy of the system. And here the surroundings and environment also plays a very, very important role whenever you are defining the exergy, because I just now I told you that exergy is also called as the availability or the maximum work potential. So the work potential is basically related to the dead state. So this the dead state plays a vital important role whenever we are talking about the availability concept. So what do you mean by the dead state? So that is when a system is in thermodynamic equilibrium with the environment, denoted by a subscript 0. That is whenever we are having P naught, V naught, T naught, that is the pressure corresponding to dead state condition. Volume corresponding to the dead state condition is V naught. Temperature corresponding to the dead state is the T naught. So P naught, V naught, T naught. These are the three important thermodynamic parameters normally we are using in the thermodynamics. So at this point, no more work can be done. So whenever the system approaches to the dead state, so the work capacity or the work potential is ceased. So no more work can be done at the dead state. Whenever there is a deviation from the dead state, so then the work potential can be improved. So the work potential can be improved only whenever the system is deviating from the dead state condition. But whenever it is coming to the dead state condition, so the work potential or the work producing capability will be ceases, and it will be zero whenever it attains the dead state condition. So that's why the dead state is a very, very important one. So the same thing here I have written about the exergy concepts. So that is availability and unavailability. So here I've already told you that whenever you are having the heat engine, the heat input is the Q1 and heat rejection is the Q2. How much amount of the heat is rejected by the heat engine, that is the Q2, is nothing but unavailable energy. And what is the maximum work which is produced by the heat engine, that indicates the available energy. So this is the concept about the entropy and disorderness of the system. So already we explained clearly, because whenever the disorderliness increases, automatically entropy also increases. So the third law of thermodynamics states that at absolute zero temperature for a perfect crystalline substance, the entropy value will become zero, and available energy is nothing but is a maximum work which can be extracted from the heat engine, and unavailable energy is nothing but how much amount of the heat is rejected by the heat engine. So with these important concepts, so in the next classroom discussion topic, we will study in detail about the availability in a steady flow process and non-flow process, Gibbs function and Helmholtz function, like that. I hope you understood the concepts of available energy and unavailable energy. So we will meet you in the next classroom discussion topic. So thank you one and all for listening this lecture. Thank you.